Hi, I'm Ethan Tang.
And I'm Brian Kellermeyer.
And then Ian's over there. And this is Lab7 interference.
For Opti380A.
Hi, this is Ethan. This is the young double slit part of the lab. So what we're doing is we're finding the fringe spacing for our boss. We took this laser and shot it through the little double slits, and we put it into the camera, which then led up to here, which is where the slits would be showing up fringes. And then we measured the fringe spacing between the slits. We took this and we moved it away from here to see fringe spacings, and then we did it for two different types of double slits to see how that would affect the results.
The difference in the slit spacing should have had no result on the data, which we have shown by using slit A and slit C, which had the same slit spacing but not the same slit width. And so, upon our results, our slope is 1 over the distance in between the slits. And so, when solving it, we got the slit width to be 0.257 and 0.255 millimeters.
So this is part B, Lloyd's mirror, which we use interference patterns to measure the wavelength for the laser. So the way we did this is we took the laser and we used this mirror along with this gauge to measure go through the detector and then measure this fringe pattern right here, which then what that allowed us to do is to put this into MATLAB, which then eventually measured the pixels of the spacing, which then calculated our fringe spacing.
We got a linearly fit line that shows very little spacing. It's very hard to see, but these little dots along them are actually our error along the line. And so we got a wavelength of 690 nanometers, and which is a little bit off from what we should have got. And I think the main source of error in this is that we used the tape measure to measure from the pinhole to the detector when we should have most likely used triangle to find the actual hypotenuse, which would be a much more accurate result.
So this is part C of the lab. What we're doing is using these wire dippers to create interference patterns both in phase and out of phase, and then we're going to compare those with the actual results of the data. So that we did this by changing the frequency of this thing.
The in-phase data is very similar to the theoretical result, as there is a linear straight line in the middle, as well as hyperbolic functions created along the interference pattern. Out of phase, they have reverse contrast, where there is not quite a straight line there, and it would be equivalent to the in phase, except now the dark parts of the fringes would be highlighted as such. It's also interesting to note that the out of phase information relates to the Lloyd's mirror experiment, while the in phase relates to the Young's double slit.